What's a group? A group is a mathematical structure defined by certain properties. So first of all, what's a mathematical structure? A mathematical structure is just a set with some operations on this set. And a group is a non-empty set, G, together with an operation on this set. I'll call it star here. So star is an operation which takes two elements of G and gives one element of G. So if it's a well-defined operation, takes two elements, gives one element. Like for example, the sum or the product in the field in R or in the nature numbers. Just an operation like this. And star must have the following properties. It must be associative, which means that for all x, y, and z in G, if I write x star y, and then I do this new element of G, I do it star z, I will get the same thing as if I do y star z first, and then I do star x to the left. So this means, in fact, also that I can write just, if I have this property, I can write x star y star z without parentheses, and it makes sense. A priori, it shouldn't make sense if I don't have associativity, because it could mean two things. It could mean this or this, because star is an operation between two elements, not three elements. So I have to say which two I do first. But if those two are equal, so I can just remove the parentheses and understand that x star y star z is just any one of these two possibilities. The second property for a group is that it should have a neutral element. I'll call it E and G. What's a neutral element? So it's an element which has the following property. For all x in G, E star x is equal to x star E and is equal to x. So this neutral element, when you combine it with another element of G, it doesn't change this last element. Think, for example, of star as being, let's say, plus. The plus we know in R, and the neutral element is 0. For all x, x plus 0 is x, and 0 plus x is x. Or if you want, think of the operation being the multiplication, and the neutral element is 1. The next property a group should have is the existence of inverse elements for each element. And says that for any x in G, I should have an x prime also in G, such that x star x prime equals x prime star x and equals the neutral element E. Like for example, think if G is R, the real numbers, and star is the sum, so the neutral element is 0, and the inverse of x is minus x, like the inverse of 5 in this case is negative 5. Because 5 plus negative 5 is negative 5 plus 5, and it's just 0, which is the neutral element. One other property, I said it at the beginning, but I'll write it down. So it's closure, the closure property, which says that if I take any x and y in G, combined together should give again an element of G. It shouldn't be something undefined or something outside G or whatever. It's a well-defined operation, well-defined application from this set to G. If moreover the operation is commutative, like if I have for all x and y, x star y equals y star x, I say then that the group is abelian or commutative group. But this doesn't hold always for all groups. So these are the properties which define a group. And those are the unique properties. So what's the nature of the elements of G? Are they numbers? Are they sequences of numbers? Matrices, whatever? We don't care, in fact. It could be anything. They could be chairs or any set of things on which I have these operations. the nature of the elements of G usually often is not important. It's like when you play chess, you wouldn't ask if the queen corresponds to a real queen, or if the knight corresponds to a real knight, or to something else. It's just not relevant for the game. It's not important. The only important thing is what are the rules. And it's the same for a group. The group could be anything, and the important things are the rules, and these are here the rules. So examples for groups: Z together with plus is a group. It's easy to check. Plus here is just the usual plus, the one we use in Z. R with plus, C with plus, Q with plus, all of them are groups. The neutral elements in each of these cases is just the zero element. The inverse of x is minus x, and the operation is well defined, and we have associativity, so those are groups. Why don't I write n with plus? What do you think? So n with plus is not a group. It has associativity and a neutral element, and has closure, but doesn't have inverse elements, because the neutral element is 0, and I can add nothing to 2 to get 0 when I work in n. This doesn't exist in n, so n with plus is not a group. A third example: what would you say about R, for example, with multiplication? Is it a group? Multiplication is well defined. It takes two elements of R, gives one element of R. So we have closure, we have a neutral element which is 1, we have associativity, but we have inverse elements. In fact, no. Well, we have always inverse element, except for one element, which is 0. 0 doesn't have an inverse. There is nothing that you can multiply with 0 to get the neutral element, which is 1. The same, I can say it about C with multiplication and Q with multiplication. Those are not groups for the same reason. But what if I remove this 0? If I take R star, like R without the 0, the non-zero elements of R, with the usual multiplication. So this one is a group, because here every element has an inverse. If x is in R star, I can calculate 1 over x, because x is not 0. And 1 over x times x is the neutral element 1. And the other properties hold. I can say the same thing about q star with multiplication and c star together with the usual multiplication. Those are groups. Now all the groups I gave here are infinite groups, but do we have finite groups? Yes. If I take any n, any non-zero n, the integers modulo n, which I can write them down like the elements 0 bar, 1 bar until n minus 1 bar. This is the set, and the operation is plus bar, addition modulo n. This is a group. It's a finite group. It's a group which has n elements for every n, so I can find a group which has exactly n elements. The associativity holds because it holds for the plus and z, and you have this compatibility. The neutral element is 0 bar. The operation is well defined, and every element has an inverse. Like the inverse of 1 is n minus 1, the inverse of 1 bar is n minus 1 bar, the inverse of 2 bar is n minus 2 bar, etc. Now what about the integers modulo n together with the multiplication, which we defined on them? This, in fact, cannot be a group for the same reason for which R with multiplication is not a group. 0 bar is not invertible. Here, in this case, for this operation, the neutral element is 1 bar, and 0 bar is not invertible because you can multiply it by nothing to get 1 bar. If you multiply it by anything, you'll get 0 times a bar, which is always 0 bar. It's never 1 bar. But what if I remove the 0 from this set. I take this set without the 0 bar. Is it a group? For every non-zero x in this set, I can find a multiplicative inverse, a modular multiplicative inverse. In fact, it's true if and only if n is a prime number. Is a group if and only if n is prime. This basically because of the Bezout identity. In fact, if you take any a bar, let's say, in this set, so a is some integer between 1 and n minus 1. The question is, does there exist a b bar in the same set such that a bar times b bar is 1 bar? The thing is that a is between 1 and n minus 1. And if n is prime, I'm doing one direction of the proof now. If n is prime, then a and n are co-prime. The greatest common divisor of a and n is 1. Why? Because a is just between 1 and n minus 1 and has no prime factors except n itself. By the Bezout identity, I can find integers u and v such that u times a plus v times n is 1. This equality is true for the numbers in z. And now when I reduce it modulo n, I get this. U bar times bar a bar plus v bar times bar n bar equals 1 bar. But n bar is 0 modulo n, so this is 0. And so I have a u bar such that u bar times bar a bar is 1 bar. So the inverse exists. The inverse always exists if n is prime. For every element a bar in this set. So if n is prime, it is a group. The other properties hold, we check them. And the other direction is also true. Because let's say if n is not prime, I can write n like n1 times n2, both of them strictly between 0 and n, so not equal to 0 modulo n. And I say n1 bar not invertible. Why? Because if it were invertible, I can come back to this equality. I write this, and then I multiply by the inverse of n1 bar, which could be some a bar, and I get a bar times bar n bar is equal inverse of n1 bar times n1 bar is 1. So I remove it from the equality, 1 bar times n2 bar. But n bar is 0. So a bar times n bar is 0 bar. But I've just said that n2 bar is not 0 bar. So it's a contradiction. Anyway, like pause the video, think about these things. It's interesting. In any case, this group will be very interesting for us if n is a prime number. Usually, for the application we'll be doing, n will be a prime number, very, very large prime number. And it's essential that the integers modulo n without the 0 form a finite group, which has n minus 1 elements. So all the groups I said so far are also abelian groups, like x times y is y times x, or x plus y is y plus x. So the star in each of these cases is an abelian operation, is a commutative operation. But do we have non-abelian groups? The answer is yes. Of course. The first interesting examples for groups was for non-abelian groups. I mean, the notion of groups were introduced by Évariste Galois, a French mathematician, and trying to solve an old problem that you have no formula with radicals which expresses the roots of a polynomial of degree 5 as a function of its coefficients. You know, if you take a polynomial of degree 2, you can express the roots. Like the roots are given by this expression. It's a formula which uses the square root plus minus multiplication and sum and division. There's a similar formula for polynomials of degree 3 and 4, but not for 5. And the concept of group was introduced to research this problem. And the groups of Galois were permutation groups. So groups for permuting the roots of these polynomials of degree 5 and higher. And permutation groups are examples of non-abelian groups. So what's a permutation group? So take any set A, let A be a set, any set, say to have a non-trivial case, cardinality of A is at least 2. If I take the bijections from A to A, let S of A be the set of F functions from A to A, which are bijections. Like F is a one-to-one map, injective. The images of different elements are different. And F is onto. For every element Y in A, I can find X such that F of X equals Y. Now on this set, I have to yet to define an operation to get a group. How should I define it? What do you think could be an operation which I can define on these functions? Composition. If F and G are two elements of S of A, F composed with G is again a bijection from A to A. It's defined by F composed of G of X is F of G of X. This defines a bijection. What's the identity element here? Which bijection, if I compose it with any other bijection, the other bijection doesn't change. It's just the identity bijection, which is defined by, to every X, it sends it to itself. And for every F in S of A, I can find G such that F composed with G is G composed with F, and it's the identity of A. Why? Because just F is a bijection. Here we use the fact that F has to be a bijection. So this is a group. The set of bijections on any given non-empty set, together with the operation composition, is a group. And it is a non-abelian group, except when the cardinality of A is 2. But you can prove, in fact, if A has at least 3 elements, this is not an abelian group. Like, typically F composed with G in general is different from G composed with F. Except in certain cases, of course, but you can find such elements F and G whenever A has at least 3 elements. Other examples of groups, for example, you can take, for example, square matrices of size n over R together with plus. And here the plus is the sum of matrices. I note everything by plus, but this plus is not the sum of numbers, it's just the sum of matrices. This is a group. The null element, the neutral element, is just the matrix where all the entries are 0. It is associative. We have an inverse of each element by inverting each of the entries, and it is an abelian group. Another group is GLN of R. It is also a group of matrices together with the multiplication. Those are the matrices of size n for a given n, for a given fixed n. I mean, any given fixed n, I can consider this set the matrices whose determinant is not 0, together with this operation, which is multiplication of matrices. This is also a group, and the neutral element here is the matrix which is 1 on the diagonal and 0 elsewhere. And the inverse of a given matrix from this set is just, I mean, you can calculate it. It has a formula involving the determinant, etc. It's not very important for us in this course, but just an example. An interesting example of a group we'll talk about later are elliptic curves. The set of rational points of elliptic curves on a given field form a group. I'll speak about this later in one of the videos. In fact, these groups, together with the multiplicative groups of the integers modulo p for p prime, but mostly these groups are the standard groups today used in cryptography. They are used for example, making digital signatures or for the Diffie-Hellman key exchange, because they are considered secure even with a smaller key size than other groups. Notations. Well, as you realized, often the operation of the group is denoted by plus or par multiplication. Many different operations are denoted by plus, and many other different operations, as we saw, are denoted by multiplication, this times. Now, if the group operation is denoted by plus, we say that the group is additive. So if I tell you, consider an additive group G, you understand, okay, so the operation of G is just denoted by plus. And an additive group, by convention, it is always abelian. It's a convention. If you have a non-abelian group, you wouldn't denote the operation by plus. You can denote by multiplication. That's how people are used to do things. Now, in the case of an additive abelian group, if I take an x in G, so the group element x plus x, etc. n times, and here, as I said, I don't have to put parentheses because of associativity. This thing is denoted, it's just a matter of notation, is denoted by n times x, where n is a natural number. If I tell you 3x, you understand I'm speaking about the group element x plus x, where plus is the group operation. 3 times a matrix A is just A plus A plus A. Now, another notation, the inverse of x is denoted by negative x, just the notation you are used to. Negative x is just the inverse of x for this group operation. Now, another notation, group of notations, is for the multiplicative groups. So if the group operation is denoted by times, by multiplication, we say that the group is multiplicative. In this case, the neutral element is denoted by 1. Or, in fact, one index G if there's some confusion. The inverse of an element is denoted by x to the power negative 1, like the usual notation. Above, I forgot to say that for the additive case, the notation for the neutral element is 0, or 0 index G, if there's a confusion on G. And now, if I take an element x of a group G, a multiplicative group G, and I apply the operation x times x times x, etc., n times on this element x. So this element, I get an element of G. This element is denoted by x to the power n, where n is just some positive integer. X to the power 0 by convention is the neutral element, and x to the power negative, a negative number like negative 5, we understand it as x to the power 5 to the power negative 1, or x to the power negative 1 to the power 5. And it's the same thing. This is the same thing as this. Now, what's a subgroup of a group? A subgroup of a group is a subset of this group, which itself, again, is a group. So it has to contain, in particular, it has to contain the neutral element. For example, I can say Z with plus is a subgroup of R with plus, where I understand this plus as the restriction of this plus to Z. I mean the usual operations we know. The set of positive numbers with plus is not a subgroup of R with plus. Why? It's stable by plus. Plus is still associative, it has a neutral element. But the inverses don't exist anymore. So this one is not a group in itself. So I cannot say it's a subgroup of R. There's an interesting properties for subgroups of a finite group. So I can write it down here. Property, if G is a finite group and H is a subgroup of G, then the cardinality of H, the number of elements of H, which is a natural number, divides the cardinality of G. So if G has 15 elements, this cannot have 7 elements, because 7 doesn't divide 15. It can, for example, have 3 or 5 elements, or 15 elements, or 1 element. A number which divides the number 15. The cardinality of a group is called, we say usually, the order of a group. The order of H, the order of G. We mean by that cardinality or number of elements. This is called Lagrange theorem. Now what's a generator of a group? So let's say I take some finite group G, and I take an element A and G. I say that A is a generator of G if and only if every element of G can be expressed as A to a certain power. If and only if for only X and G I can find a natural number N such that X is A times A times A, etc. N times, which as we said, we denote by A to the N. Examples. If let's say I take the integers modulo 6 together with plus, the usual modular addition modulo 6. We have a generator here. I can find an element here such that the other elements, any other element is a multiple of this element. So here I have to pay attention. This plus, okay, I can remove the bar and consider that I have an additive group. The multiplicative x to the power, let's say 3, is x times x times x when the group is multiplicative. When the group is additive, this becomes x plus x plus x, just because the notation of the operation is plus. But in this case, I don't denote it x to the power 3, I denoted 3 times x. So this group, does it have a generator? 0 or 0 bar is not a generator. Because you add 0 with itself as many times as you want, you'll always get 0. You'll not get the other elements of the group. What about 1 bar? 1 bar is a generator. Because the elements of the group are 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and 5 bar. And the 2 bar is 1 bar plus 1 bar. 3 bar is 1 bar plus 1 bar plus 1 bar. 4 bar is etc. And 0 bar, I can write it always 5 times 1 bar, like 1 bar plus. Or, pardon, 6 times. Okay, 1 bar is a generator. What about 2 bar? Is it a generator for the group? 2 bar. So I see, what can I write with 2 bar? What does it generate? The 2 bar, what does it generate? So it generates the following set: 2 bar plus 2 bar, which is 4 bar, 2 bar plus 2 bar plus 2 bar, it's 6 bar, it's 0 bar. And now when I add it 4 times, I get an element I already have. So that's all what I get when I add 2 with itself, modulo 6. So it's not the whole group. There are elements missing here, like 1 bar. So it's not a generator. 3 bar is not a generator neither. Because 3 bar, when it generates the following set, 0 bar and 3 bar. 3 bar, if you add it with itself, as many times as you want, you'll not get any elements other than these two elements. So you'll not get the whole set. In fact, we have a theorem that the generators of the integers modulo n with the operation plus are the elements a bar such that, well, you can try to guess this one. Perhaps you need some more examples to guess it. So, but I write it down. You can stop the video and think about it. So those are the a bars such that a and n are coprime. What about the multiplicative group? So if I take, let's say, I want a group, in fact, so I take a prime number, for example, prime number 7, I remove 0, so I have this set, and I take it with the multiplication, modulo 7. So I have these elements, together with the multiplication, modulo 7. Does it have a generator? Let's see, here the operation is multiplication. So I have to take the powers of each of the elements. 1 bar is not a generator. Because of the powers of 1 bar, I have only 1 power, it's just 1 bar. What about 2 bar? What does 2 bar generate? If I take all the powers of 2 bar, it is a group, in fact, we can prove it. What's this group? Is it everything or a part of everything? It contains 2 bar. 2 bar times 2 bar is 4 bar. 2 bar times 2 bar times 2 bar is 8 bar. And 8 bar modulo 7 is 1 bar. And now when I multiply it by 2 bar, I get this element and then this element and so on and so forth. So I have just these 3 elements. So it's not a generator. It's not a generator of the whole group. There are elements missing. Remark here that this, as I said, it is a group, you can check it. It has 3 elements. The original group has 6 elements. 3 divides 6. This is just an instance of Lagrange theorem, which says that the order of some group always divides the order of a group. Now what about 3 bar? What does 3 bar generate? Which group? Which subgroup? I have 3 bar. 3 bar squared is 9 bar, which is 2 bar. When I multiply it by 3 bar, I get 6 bar. And when I multiply by 3 bar, I get 18, which is 4 modulo 7, times 3, 12, which is 5, times 3 is 15, which is 1 modulo 7. Times 3, I get back to here. So all the elements of the group can be written as powers of 3, so it is a generator. I let you check the other elements, 4, 5, and 6. If they are generators. And for this question, if I take any prime p, and I take all the non-zero integers modulo p, together with the multiplication, like the example above with p equals 7. We said that this is a group, and there's a theorem which says that this group always has a generator. It's called the primitive element theorem, because the multiplicative group of a finite field always has a generator. This is a theorem. So you can, with that, try to find a generator for example, the integers modulo 11, which are non-zero.